Okay, so we have a MacBook Pro. It's A2141. A2141s are the first 16 inches lineups for the Mac for the notebooks, and it was first introduced in 2019, and it was only refreshed with the 2021 16 inches M1, which was a redesign, a complete redesign of the 2141. Was the M1 16 inches, and also the 2141, the 16 inches was also the last time they used, in terms of the 16 inches, that's the last time they used the touch bar strip, and because the redesign of the M1, the M2, the M3, and as well as the M4, which is the current, has no touch bar. So this is the 2019 form factor of the 16 inches, and it's coming in for no power. So this one, Shaheed has assessed it. He obviously he made a couple of measurements, and then but he was still busy with it. But then I decided to take it over just to see how I can speed up the process. So he already took out the board. He made his measurements. So I'm just gonna take it just I will start from scratch, and basically just walk you guys through how you typically go over a device like this one. So like I said, the screws are out, and usually when I get in the device like this one, the first thing I'm going to do is I take out the back cover. The next thing I'm going to do is I'm going to disconnect the battery cable. Now just a small note regarding the battery and the battery cable. So the battery has two communication channel that is established, that it creates a communication with the board. So the first channel, it's the cable, which is the data cable, this guy here, that's the data cable. So the data cable makes its way from the battery board onto the main logic board, which is this guy. It is detachable. You can have it taken out from the other side. The cable is detachable. That's number one. And number two, so this is a data line, and then you have a small voltage there. It's about 3 point something volt. And then you have the main battery line, which is the main battery power line is going to be this one here. So this is going to be the main battery power line. Here you have 11 point something volt voltage from the battery, and the PV bus, which is 12.6 volt, which is what is going to come from your PV bus 2, which is the PV bus that's been generated from your board. Now, and then again, you know that the battery generates its own, provided there is a voltage on the battery. So from the battery you get about 11 point something volt, and PV bus generally is about 12.6 volt. Now in order for me to disconnect power that comes from the battery to my board, I need to just remove the cable. That suffices. But then that approach is only if I can guarantee that the battery, it's an original Apple battery. Now, if it's an original Apple battery, it follows a particular pattern in a case, in a sense that when the cable is disconnected, the power stops flowing from, basically the battery becomes inactive. However, if the battery is a non-Apple battery, so what happens is even when the cable is disconnected, the battery will still be able to, just the power, the main power line, and it will still be able to hold power to the battery, to the board. So what that will mean is even with the cable disconnected, the battery is still going to be active on the board. So which is why it's best to obviously try to, when you're getting a battery replacement, or if you're busy with this, because you don't want to have power present on the board while you're busy with it. So what you want to do is you want to make sure that the battery is disconnected. Now, just for you to be sure, if you're not sure whether it's an original Apple battery or not, just make sure to remove the battery screw, which is this guy here. So the battery screw basically is what allows communication to be established between the main battery line, which is this guy, and the battery board. Yeah. So you have your, so there you have your minus, and then you have your plus, positive basically, and your negative. So with the long screw, that screw there, it's what allow communication to be established. So the screw is supposed to enable the communication. And then again, sometimes you might just decide to just loosen the screw just a little bit. But when you're putting the device together, sometimes you tend to forget. So when that happens, obviously the battery is not going to be detected. Okay, so like I said, if you're not sure if the battery is an original Apple battery, just to be on the safer side, remove the what? The screw. And then I say another thing is this is a very unique screw for the 16 inches. The one time that Apple used such a long screw for their battery communication was also the F1425, which is the 2012 MacBook Pro Retina. That's basically like the first Retina in terms of the 13 inches that Apple did. 13 inches Apple, the first Retina that Apple did was A1425. They also used a long screw for the battery communication. And then consequently, the others, they use a short screw, and 16 inches was the only one that had a long screw like this. And then obviously after the 16 inches was discontinued, with the redesign of the 16 inches, they went back to the smaller screws. When I mean smaller screws, I'm going to see if I can find something for you guys here. It's relatively shorter compared to, so that's the standard screw that they use, and this is only for A2141, and this is what they use across 2013, 2014, sorry, 2016 down to 2024. This is the screw that they use for the battery communication, main battery communication to the battery board. And this is the one that this is for 16 inches and 16 inches only. And even the one for F4120, F1425 is completely, it looks completely different from this. Okay, so that's that. Let's continue. Now, typically what I would do is with the back cover out, the battery disconnected. The next thing I'm going to do is I want to see if I have a short. So the first thing I'm going to do, I can use continuity mode just to see, to get the beep, but I'm not going to use continuity mode. I prefer to use diode mode. I'm going to switch to diode mode. So I'm just going to show you guys that is continuity mode. In continuity mode, you will hear a beep if your multimeter is a type that does that. But I'm going to be using diode mode. So with my diode mode, I'm going to have my red probe to ground, and then I'm going to use my left probe for my reading. So I can either use that or I can use that for my ground. So I'm going to start from my PP bus line. Let me see what is it that I have on PP bus. PP bus is 0.4 something. That's about okay. That's about what I'm expecting. I'm going to check. I'm going to now check on my 2.5 volt lines on both sides. The 16 inches has two wings, or two SSD wings, the right and the left. Both will have both output will be 2.5, 2.5. So I'm going to check on my right, which is this one here, to see if I have any short on the right side. There is no short. That's about I'm expecting. And then on the left side, let's see. That's fine. That's also what about I'm expecting. Now, I could also measure the 0.9, 0.8, and 1.5, but I don't have to. The fact that I don't have a short on the 2.5 volt line, and I don't have to measure the lesser voltage. So then the next thing I'm going to do, it's typically I would want to connect the charger, but because of what he told me, he mentioned something about having because of what he told me, and I did made measurements on the board just to be sure what he said. I'm not going to connect power to it. Rather, I'm going to see. So yes, we know we don't have a short here. We don't have a short there. The next thing we're going to do is we're going to see what is it that we have on our. Uh, uh, let's see what is it that we have on our CDs. But before we do that, what we can do is we can actually connect charger to it since we don't have a short on PP bus, and see what is it that we have on our PP bus. So make sure you use the right charger for your troubleshooting. For A2141, you want to use a 96 watts or Apple original charger, 96 watts, and also use an Apple original cable for your troubleshooting. And then another thing I just want to mention is just in case you're trying to boot your machine into DFU mode, sometimes if you use a generic cable, it might not detect the device being in DFU mode. So that's also something to take note of. It will be best to use an Apple original charger just to be on the safer side. Sometimes you use it, and even though the device is in DFU mode, it will not be picked up that the device is in DFU mode. Okay, so the next thing we're going to do is we're going to connect our charger just to see what is it that we have on our PP bus. Okay, let's quickly do that. So first port, switch to voltage mode, and then let us see what is it that we have on PP bus. Usually, when you get a dance, a voltage that behaves like this, oftentimes the 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 line itself might not be an issue. However, what the line is feeding might be a problem. Sometimes it could be what feeds the line, the power rail, it's an issue, or what that rail is feeding, it's an issue. In terms of there has to be a short or a partial communication, a short to ground or short circuit. Usually not a short circuit. It has to be because if it's a short circuit, it's not going to behave in this manner. You have a short to ground, either the rail that feeds the rail that is behaving that way, or the rail or the rail that it feeds. So either in to this rail that behaves this way or out to another rail that it feeds. So say for example now we have a PP bus that is behaving that way. It could be that the rail that the PP bus feeds it's an issue, but nonetheless we'll find out exactly what it is. So let's try to see if that behavior it's repeated across the four ports. So we've tried the first port, now we're trying the second port. Let's see what is it that we're gonna have PP bus. Still the same thing. So let's check the other side of the same thing. Let's try the last port. It's exactly the same thing. So at this point, I wouldn't be blaming any of the CD3217. By the way, the 82141 uses the revision of CD3217, not 15. So I wouldn't be blaming any of the CD3217 because the four ports are behaving exactly the same way. So something that has communication with the four ports has to be affected, which is why the four port behave in the same way. So the next thing I'm going to do is I'm just going to let's see what are the let's check the LDOs of each of the CD3217. So let's check their LDOs. We have the 1.5, the 3.3, and PP3V3 underscore RTC. So let's check this. Let's check the LDOs and let's see what is it that we get. So we are gonna use U3100, not U32. We're gonna use U3100. We're going to be using U31, the CD3070 U3100. That's the one that we are going to be using. Okay, so let's check on the LDOs, C3104, 3108, and C3200. Okay, so that's going to mean this, and that. Our multimeter is set to voltage mode. So we have our black probe on ground, and then our red probe is that from the 1.5 volt line. What we have 1.5, that's good. 3.3 volt line, that's good. We have a 3.3 volt, and then the other one, which is okay, PP3V3 underscore RGC. Okay, that is not being created. Okay, yeah, I think that's we see our problem now. Now you see the 3 volt is fine, the 1.5 volt is okay, but the sky is not being generated. Now the RTC is generated from our that's a rail that is generated from the PP bus rail. So it makes sense why the device not only does not power on, also why the PP bus was behaving the way it's behaving. So what we are going to do is we are going to quickly take the board out and find out why this one is not what it's not being generated. So let's take the board out. Good thing is the screws are already out, so we're just going to disconnect the cables and take our board out. Do you have any questions so far? Yeah, okay. Yeah, I mean, when you start to make the measurements, you have to check the LDs because usually the LD, and obviously the reason why we have to worry about the LDOs is because we don't have 20 volt. If we had 20 volt on our PVDC, we wouldn't worry. the fact that we're getting the fact that we don't have the RTC means that we are going to have 5 volt on the line. So I'm just so that you know, I'm just going to show you that you are not going to have 20 volt because RTC it's a crucial it's a critical requirement for 20 volt creation. So without RTC, you're not going to have 20 volt. You're only going to have 5 volt. Okay, did you check? Okay, I'm just gonna confirm. Let's see, 5 volt. Yeah, so you because RTC well is required for your 20 volt negotiation. So without it, you're not going to get 20 volt. So let's take the board out and find out why is it that the board itself we don't have the RTC well. Usually, what we would do in a case like this is we are going to do a scan on the board. But then because we know that because we already have a point of interest, we are only going to focus on the RTC line. So let's see what is it now. Just something that I need to mention. So I'm not, even though you can clearly see that the RTC is represented across the 4 ports, correct? Across the CD3217. So you have it represented on U3100, U3200, and then on the other side of the board as well, which is UB300, which is also the CD3217 and UB400. However, I'm not really, in terms of, I'm not really going to be looking into the CD3217. Why? Because if any of them was an issue, I'm thinking that I should get a different behavior from that one that has an issue. But in this case, I'm getting the same behavior across the 4 ports. So I'm not going to be really looking into the CD37. However, I'm going to be looking into the capacitors by the CD32 17s, the ones that are just by, because I mean, in each of the RTC line that are connected to the CD3217, you will find a capacitor that is closely attached to the CD3217. So those capacitors are what I'm going to be looking into first. So oftentimes, I mean, sometimes you will find that one of those cap would have failed. So, but then again, that if it fails, it means we should have a short on that line. So let us see if we have a short on that line. We should actually explain why our PP bus behaves the way it behaves, because PP3V3 underscore RTC is generated from PP bus. Now that takes place here. That takes place here by U6960. Let's quickly open up the schematic. A20, A20, A20. Now what am I doing? A20 dash 0001 700. Okay. Let's quickly go to the guy here, U6960. Okay, let's search for U6960, U6960. So it says it says 3.3 volt G3H. And remember when we said G3H is what? Always present. So that has to be present. And it says and then it says VR, which is voltage regulator. Yeah, so VR is voltage regulator, 3.3 volt G3H. I mean, this defines basically to tell you that that rail has to be present at all times. Now, if we look at the way this obviously says the chip itself is critical, it's a BGA chip, yeah. And then and if you need to buy this chip, for example, this is you can use this description of the chip, TPS 62180, if you're going to buy the chip. Now, if we look at this chip here, we have a couple of enables, and obviously we are going to have a couple of input, and we're going to have outputs. And usually you will see that when it comes to, okay, when we do more into voltage creation or regulation, then I can really talk about the switching and how it actually works. But it suffices to know here that you're going to have voltage in, and then you're going to have, so this is a buck converter. It's going to take a high voltage, correct, and turn it into a low voltage. Now, this is the high voltage that it's going to take. It says here 13.1. Roughly, you get about 12.6 for your PP bus that comes into. So where it says, you see where it says V in, you have a couple of V ins, ones, and then you have VE2s. Now it's going to take a 13.1 volt, but like I said, it's a 16 point, it's a 12.6 volt that will go into the chip. Then it's going to output what? It's going to output a 3.3 volt, correct? So it's a buck converter. It takes a high voltage and turning it into what? A low voltage. And obviously it does that through switching, which is why here you have SW1, which is switch, yeah? And then you have the LW2. Now, and then again, here you have voltage. You definitely going to have feedback. It's going to have a feedback line. Now, the whole point of a feedback line, it's basically for there's so much that the feedback line does. However, one of what basically happens is after that voltage has been created, the feedback line allows the chip to obviously self-regulate, to know that when the what when you have when the voltage has been generated and is also obviously stable. And also again, for example, if you tend to have a short on this line, the feedback line will also be able to report to the chip that you have a short on that line, and then obviously which would then allow this to turn itself off. The feedback does so much on a chip, and basically your feedback is basically like a driver, which the eyes of a driver is basically what your feedback. It's like basically the work of your feedback. For example, when you're driving and then you see an obstacle on the road, your eye is what sees it, and then you now apply the necessary measure. Okay, so we have in, and then we're going to have out. We said this is a buck converter. It takes a high voltage and then it turns into a what? Into a low voltage. Now, it's not enough to have a voltage in. You have to have a switch, which is a switch that turns the chip on or off, which is what is referred to as the enable signal, correct? The enable signal is what it's going to tell the chip to either be on or off. Without the enable signal being present, the chip, even if you have voltage in, nothing is going to be on out. So so you're going to have so you see where it says so charger enable MVR. So you will have a resistor here. So basically, you're supposed to have a signal here that basically tell the chip to do what? To be on. So let's not dwell so much here. So basically, we just want to know why the 3.3 volt RTC is not being present. But first, let us see if we have a short on that line, because that will explain why the PPV in voltage, which is the PP bus voltage, is behaving the way it's behaving. So let's go to U6900 and we can check L6960 and L6961 to see if we have a short. Those are the inductors that are attached to your U6960. You're supposed to get your output of the 3.3 volt from those inductors. So let's go to the board view, which is going to be, let's just confirm, L6960 and 61, L6960, okay, this guy 60 and 61. Okay, let's see what is it that we have. Obviously you see that. Those are the two, correct? Okay, let's see what those are inductors. So let us go and find out where those are on the board. Let's just flip the board. Okay, let's flip the board this way. And obviously you guys know why we're here, because when we check the LDOs, we found that the ROTC is not present. So let's see. Let's check first to see if we have a short on that line. We're going to use diode mode. So our left probe on ground, and we'll just put this here to make it easy for you guys to see. Because we're using diode mode, I'm going to use my red probe on ground and then my black probe. This is the two here, L6960 and 6961. So let's see what we have. 003, that's very low, and the other one 003, that's extremely low. I'm just show you guys what we're supposed to have there. This is a non-working board. This is what you're supposed to have on that line. 0437. That's what you're supposed to have on that line. So and then so like I'm very sure that yeah, so I'm very sure that's why the PP bus was behaving the way it's behaving. So we are going to resolve that, and then most likely PP bus will be fine, and that should actually resolve, hopefully. Oftentimes when you narrow down a particular issue, you only have one issue. Once that is resolved, you resolve your problem. But sometimes you have more than one issue. But in this case, since it's not a liquid damage device, most likely this will be the only issue that is going to have. So, like I said, what we are going to do is we are only going to be looking around the capacitors that are not only, but we'll start by looking around the capacitors that are attached to the CD3217. So if we click on, so let's see, let's check the output. And then another thing we can also do is this. So here so another thing we can do is we can remove L6960 and L6961 in order to find out which side of the board the short is. So if we remove these two, and now we are obviously now this is going to be more like a bridge now. If we remove it, now you have a separation between pin 2 and pin 1. So pin 1 is going to be the generation side, where the 3.3 volt is being generated from, and then pin 2 is going to be where it's feeding the logic board. So we can remove this two just to see where that short is coming from, to see if it's the chip or on the system side. But most times, if the chip itself is damaged, what will happen is you can actually see that the chip will have a physical marking on it. And this is a chip, and it doesn't look like that. You see it? The chip looks very, very good. I don't know if you can see it. Yeah, chips looks very. So usually when you have a problem around the chip, you can see that you will see like a burnt mark, which you will see on the surface of the board. You might not see, and then maybe here will look a little bit blackened, or just, it's gonna look a bit weird, but that's not what you're seeing here. So rather, what we are going to do is we are going to remove the capacitors that are the RTC, the capacitors that have RTC. Okay. So what I'm going to do is I'm going to start by removing the capacitors that are connected to the CD3217. So we're going to remove C3100, C3200. So, and then we are also going to go to the other side of the board and do the same thing. So we are going to start from there. Actually, let me see. This look a bit off, this guy here, but let me see if that is RTC. Let's see if that's RTC. Yeah, that's RTC. The CB300. So which is this guy? It looks a bit off. Yeah. I don't know if you can see it. If you can see the size, it looks a bit off. So I'm gonna start by. I can use a tweezer just to just to remove it. But then again, when you're gonna use a tweezer, you have to do it in a way that it doesn't damage the pads. So I can just do this. So in situation where I probably don't have, even though I have a hot air, but let's say I don't have a hot air, I can just do this. Okay. I just took out the cap. Okay, the cap is out from there. I'm gonna just put on my soldering iron because I'm gonna need that. The cap is out. I'm just gonna check again because that capacitor was not looking good. Left, red probe on ground, and then let's see this. What do we have? Okay, that's not our problem. We still have it's still low. Okay, we're gonna put that back. Not a problem. So I just that didn't look so good. Okay, so we definitely still have a short on that line. So now we are going to remove, okay, CB300 is already out. Let's now check CB400, which is this guy here. We're also going to remove that. So what we're going to do is we are not going to remove it. We can just move the capacitor on the side. Oh, we can remove it, whichever. Okay, that's out. So what I'm just going to do is I'm going to read the capacitor itself. Because it's a capacitor, I expect to have OL across my on my multimeter. But if I get numbers, then it means that's my problem. I mean, especially if I get like zeros across it. OL, okay, that's not That's not my problem. That's fine. Let's move to the, so we can just put that back. So just put it back. Okay, that's, now the other side. Let's confirm which ones. Okay, C3100 and C3200. Okay, C3100. So basically the first and the first. Okay, so it's gonna be this guy here and this guy. Okay. And another thing, another way we could do this, we could also inject voltage. So it's also something we could do. Okay, that's out. Let's quickly measure the cap. See if we have. Let's see what we have across it. Okay, so OL means the cap. It's fine. That's not our problem. So now we only have one cap left. Okay, let's put that back also. Okay, we only have one left. It would be really good if that's the one that's failed. Helps save us time. Okay, it's the last one. Let's see. Did you see it? Yeah, okay. Yeah, okay, it was OL. Okay, it's fine. We can just measure on the board. Okay, isn't this, yeah, let's see. Yeah, OL, that's not our problem. Let's just confirm that. Yeah, it's not our problem. Okay, so now we now have to look to find out exactly what the problem, what the problem is. So we had to do that because sometimes you will find that one of the capacitors fails. Okay, now where else can we look? Where else can we look? Okay, so that, wait, okay, just hope. Okay, so we have a current sensor resistor here in the form of R5600. Can we remove that and see if, so R5600, so let's see if anything connected to it might be a problem. Is this cap and this cap, let's see how do they look, this guy and this guy. They really don't look bad. Okay, what else is connected on that line? What else is connected on that line? If we don't find it, we might have to inject voltage, but let's see what else is connected on that line that's of concern. Okay, we did remove that cap there, and then on the other side, let's see, let's check the other side. Starting from here, we already did those caps. And here, okay. Mm, mm. Okay, we're looking for any, because usually you look for capacitor that has, okay, let's see what this capacitor looks like. C3540, yeah, let's see what that capacitor looks like. C3540. Is it even on the board? C3540 is gonna be, is it this guy? Yeah, it's that guy. Let's remove it and see if that could be the issue, even though we doubt, but yeah, let's see. But wait, this guy don't look good. You see that? What is that? Let's see what's on that line. What is that? That's, yeah, that's maybe 3 underscore RTC, correct? No, 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 G3H. Yeah, that equals to, remember the other side, it equals to RTC. Yeah, equals to RTC. Okay, that could actually be our problem. So let's remove that guy, because that doesn't look good. This capacitor here. Yeah, that doesn't look good. Yeah, yeah, that definitely doesn't look good. Okay, sorry. Uh, let's hope that's the problem. Alhamdulillah, that's the problem. Yeah, that doesn't look good. And obviously, I mean, even though that's not RTC, but it's generated from RTC, so from which is from this other side. So yeah, so it's generated from R600. We are not going to put that back. No, we're not going to put that back. So there's no need to put that back. So, but then we are going to put back the other one. Yeah, if we want, we could put it back, but there's no need to do that. But what we want to do, it's what's the story here? This guy's not looking so good, especially that cap there. I think it would be best to replace that, even though we don't have a problem there. But if we don't replace that, chances are in future we might have a problem. And don't forget, when you're putting it back together, to clean the edges, eh? So 2.5 volt line for the SSD. SSD looks a bit. Obviously, when you're working in this area, be sure not to hit your NAND. Okay, this guy here. This guy doesn't look good. Okay, that's fine. And we're still gonna clean it just to be sure. And the other capacitor that we removed the first time, it's the other side. Yeah, this one. Okay. Doesn't have to be from the exact same sport. You can take obviously from a different board or a different sport. Just have to consider the package of the capacitor. And then if we want, we can also put this back. But if you're gonna pull that back, you obviously have to be very careful because that's close to the NAND. But we can put it back. Don't have a problem putting it back. But and I just need to stress that even if you don't put it back, you're good to go. So we're gonna take one from the same. This is the board that we obviously, yeah. You can take one from. No, not this one. Did you take? Come here. Because that's a working board. You can take from here. Obviously, what I'm gonna do? Did I just drop it? Yeah. Okay. So what I'm gonna do is I'm gonna face my hot air away from the NAND like this. I'll point it this way. So you see, but if you're doing this and if you're not very confident, you don't have to replace it because you may basically damage your NAND, which would then mean you have to remove the NAND and then rebuild it, and then obviously put it back. If that happens, you don't have to replace the NAND. You just have to remove the NAND and then resolder it because if you replace the NAND, then you have to replace everything else, all the NANDs, because the signatures will not be the same. This- Okay, so let's test again. You know, our PP bus was obviously unstable. Now let's see what PP bus will be. We were expecting to have 12.6 with PP bus in working state. Yeah, that's a good one. So I see. So which means, yeah, the issue was definitely the RTC line that was affected. So now let's put the board in a shell quickly and see. Most likely, we should have a working device. So there's something that I need to mention, which is what I was telling him. So this section of the shell here usually gets very dusty, which then creates rust on the board in terms of oxidation, and it tends to affect the capacitors on the edge of the board. So whenever you are doing any type of repair, before you put the board back, just make sure you clean the inside, especially this section of the board here, the shell. So he's gonna do that obviously before the device it's put together. But for now, we just want to test to see if the board works, and then yeah. Do you have any question? Hmm? Okay, we are going to connect only the cables that we require for the testing. Keyboard, trackpad cable. If we were using a lower charger wattage, if we're using a lower charger, a lower brick, we might want to connect the battery. But since we have a 160, 140 watts, so that suffices. It's we don't have to connect the battery to put the device. So if we were using like say for example 87 watts for example, then we need the battery to supplement our power. But in this case we're using a 140, we don't need the battery, so we're just going to connect the charger and see what we get. So we have the screen connected, we have a DCI connected, we have trackpad connected, we have a keyboard connected, fans, yeah, fans both connected. Usually one of the good sign is yeah, so that's good. Yeah, so device starts. What do we have on the screen? It's good. The fact that we have an Apollo when it's loading and hopefully it doesn't loop or shut down or crash. I mean, that is good. I mean, that tells us that SSD, that section of the SSD NAND that we were heating around, that is still in good shape. Okay, yeah, as you can see the device. So I just want to see that it loads to desktop and it doesn't crash, just just to be sure that the NAND itself is fine. So you hear the noise at the fans, so you also make sure you clean the fans when you are finalizing the repair. We have trackpad feedback. We expect the fan to be loud because the battery is not connected. Yeah, fans coming loud. Okay, we just want to be sure that it does not crash. Okay, yeah, it's a good thing it doesn't crash. Yeah, okay, yeah, doesn't crash. Okay, fan is loud, but that's about it. Okay, that's about it, guys. Thank you so much. I will see you guys in the next one. So what Shahid is going to take over from here. Analyze the repair, do the necessary testing, and then this goes back to a happy client. Thank you guys. I will see you guys in the next one. If you guys have any comment or question, you can always put it in the comment, and we will try as much as we can to answer. Thank you so much. Bye for now.